so the last lecture will not deal with the cavity QED experiment with the Rydberg atoms and the microwave photons, but it deals with the presentation of a topic which is a new project in our group, is another use, another application of the Rydberg atom, which may be very efficient, we hope, very efficient tool for performing quantum simulation by using such kind of setup where the circular Rydberg atoms are supposed to be trapped, are supposed to have their spontaneous emission suppressed by the structure of plates around the atoms, allowing, hopefully, for performing quantum simulation with a time scale which could be kind of unprecedented. So the goal will be to present you in more details the various elements of this and the goal, the kind of things one can simulate with this Rydberg atom simulator. So before going into the Rydberg atom simulator, let me just very briefly introduce the field, which I guess is also introduced by the lecture of Juliette. So quantum simulation is one part of the now very famous quantum technologies, and indeed its development can be related to this remark by Richard Feynman, stating that, okay, if you want to do something and predict the behavior of a quantum system, the best way to do is to use a quantum system itself. So why indeed simulating then a quantum system with another quantum system? Why not just use the initial one? Indeed, the point is that for many complex problems of quantum system, especially many-body physics problem in solid-state physics, you have the system, but usually the degree of control of this system is eventually not as high as the degree of control that you can get with artificial system used to mimic the actual solid-state system. So more specifically, the quantum technology allows now the manipulation of many different systems with many well-controlled particles like ions, atoms, molecules, or Rydberg atom, as I already mentioned. And indeed, when you build a simulator out of this well-controlled particle, you usually have some knob to adjust the parameters of your simulator that you eventually do not have in the original system. So I will show you some examples for the Rydberg atom simulator. The other point is that once you do the simulation, you can eventually measure individual particles if you simulate your process with well-controlled individual particles that you can measure one by one, and then you can access to some observables that you never access in solid-state devices. You don't count electrons one by one in a solid, and the measurement of correlation functions may be tricky. When you measure the quantum state of each individual particle, then you access directly to all correlation functions of the system, which are important parameters to characterize the physics of many-body systems. So that's the concept of building a quantum simulator, and I think that presently this field has a strong development on many different platforms, and one reason for that it is probably easier. So easier does not mean easy, but it is probably easier to build a quantum simulator with respect to a quantum computer. Quantum computation needs basically quantum error correction, which is an extremely difficult task to achieve. Quantum simulation does not, and it's closer to analog computation, to have a system which processes in an analog way instead of a numerical way in order to mimic, to simulate the system you want to study. So let me now be a little bit more precise in specifying one of the reasons for building of a quantum simulator, which is the efficiency of a quantum simulator with respect to classical simulation. So let's consider the simplest elementary system, let's say a spin or a qubit. Then it's simple, and all of you can compute everything on the evolution of a single spin. So if you consider 3, it's a bit more complicated, but if you work a little bit, you manage to get it even with a piece of paper. If you have many, then it becomes very difficult. And if you have a macroscopic sample of matter, it's completely impossible. So why is it impossible? It is related to the exponential size of the Hilbert space in a many-body physics. If you have two-level system, you take n two-level system, the number of states in your Hilbert space is 2 to the n. So it's exponential of n. And as everybody knows, an exponentials go up very fast. So here to illustrate this with a simple tool, so you probably most of you can use MATLAB on your personal computer. So if you want to give MATLAB the task to diagonalize a matrix, here I represent as a function of number of spin involved in the Hamiltonian, the duration, the diagonalization time of a matrix, typical matrix of dimension n, 2 to the n times 2 to the n. So for n equal 10, with even a laptop, it's only 7 seconds. For n equal 30, which is not much, it's already 3 hours. So from seconds to hours. For n equal 16, it would need 8 months. And for n equal 40, like 4 10 to the 25 years. So I'll let you, don't even try to imagine how long it is. So of course you can say, okay, but this is just with a laptop, you can use a supercomputer. Yes, you can. But if you do, you manage to diagonalize the system for maybe 35, 40 particles, and then even the biggest machine just stops. And 40 particles is not much. And that's related to the fact that an exponential goes really fast. So if you want to fight against exponential, going from laptop to superconductor is not enough. And then if you want to learn about systems with a larger complexity than that, you have to find other ways. Of course, there are many ways. There are approximations, and physics is based on approximation, on finding the relevant parameter of a problem to estimate it. But indeed, at some point, there is a limit of this approach, and it would be very nice to compare the model, the approximation, with a real system, let's say, a simulator. So here is a remark about the state of the art I already mentioned. So basically, supercomputer can exactly deal with up to a few tenths of spin. Approximate method I mentioned are eventually more powerful for more specific tasks as just resolving the Hamiltonian. For example, if you are just interested in finding the ground state of a solid-state physics system, you have very powerful method, especially in one dimension, so-called DMRG, which is basically efficient to find the ground state of any kind of system. So this problem can be considered as solved. But if you go into more excited states, it becomes tricky. And if you go to dynamics, where you involve a lot of the excited state of the system, then it's very difficult to make prediction. So, and then also, it's difficult to make predictions and simulation with computer over extended period of time. So the limitation is the size of the system, the time over which you can eventually numerically simulate the system. And then let me go a little bit more into what is needed for realizing a good quantum simulator in a case of simple system, which is already in interest in solid-state physics, which is a chain of spin 1/2 with tunable interaction. So you need good spin, good isolated system from the environment. You need to be able to prepare the initial state of the system in a very reliable way. So you need basically to have, if you have a lattice, exactly one spin per lattice site, and usually you have to fight a little bit for that. You would really like to have long lifetime and strong interaction between your spins so that you can make the simulation, you can perform the simulation over extended time scale. And you would like to have kind of full tunability of the parameters of your Hamiltonian, which have different terms. The internal Hamiltonian of the spin, the external Hamiltonian, which means that you can apply external fields to your spins, and the interaction Hamiltonian, which indeed describes how the spin interacts in the simulator. So then there are many platforms for performing quantum simulation. I already mentioned yesterday during the colloquium. So there are platforms based on single control particles like ions, atoms, molecules, or atoms trapped in cavities. There are solid-state divided devices like superconducting circuits or single electron spin trapped and manipulated in nanoscale circuit, and I will focus on the platform based on the circular Rydberg atoms I discussed in my previous lectures. So why is the Rydberg atom interesting in this context? One first very interesting property of the Rydberg atom is the large strength of interaction between the individual qubits, which makes it nice to have kind of fast quantum simulator with a fast dynamic timescale for simulating a given problem. So here you have the usual expression of the dipole-dipole coupling representing the interaction Hamiltonian between two atoms separated by a distance r. The r is the distance separating the center mass of the two atoms, and small r1 and r2 represent the position of the electron within the atom. So with the Rydberg atom, dipole is large, as already mentioned this property, and then the coupling strength is the distance between atoms. The Rydberg atoms is not so small, 5 micrometer is much more than usually the wavelength of light used for trapping the atoms. Then for such kind of large distance, typically the strength of the dipole-dipole interaction between two Rydberg atoms is like 10 to the 11 times larger than for ordinary atom. So dipole-dipole coupling between two rubidium atoms in ground state is very, very, very weak as compared to the Rydberg atom. So 10 to the 11 times larger means that if you put one Rydberg excitation of the atom, and you look at the exchange of this excitation between two atoms, it's very fast. It can be as fast as several megahertz. So the time scale will be microsecond for the evolution of such kind of quantum simulator. So indeed, several quantum simulators have already been built and designed on the basis of the strong dipole interaction between Rydberg atoms. So the first family of experiment is depicted here with, as an example, an experiment performed in the group of Emmanuel Bloch and Christian Cross in Munich, where basically the experiment is based on the ability to prepare nearly perfect lattice of ground state atom by using the Mott isolator. So they prepare ultra cold atom in the phase of a Mott insulator, in which basically there is exactly one atom per site in the optical lattice. Then they look at the lattice. They have a way to eliminate the atoms they don't want for the simulation, and in this case, they eliminate all the atoms except the one which were just aligned in one direction. And so that's one of the first very important ingredients for controlled quantum simulation, the preparation of nearly perfect collection of qubits for performing the simulation. So this is not perfect a priori, but there is a little bit of post-selection. If you have a sample with a mistake, an error, then you try again and you restart. But the degree of control is good enough so that with high probabilities they get a very well-controlled initial state. And then they performed a quantum simulation of the dynamic, the Ising dynamic of a 10-atom spin chain. And here the interaction between the atoms is controlled by promoting the ground state atoms, which are prepared in the lattice, into the Rydberg levels, not resonantly, but by using what is called Rydberg dressing. They put a laser which is detuned with respect to Rydberg transition which mixes a little bit of the Rydberg character, of the large dipole of the Rydberg, into the ground state of the atom. So this has the advantage to increase strongly the interaction between ground state atoms without too much affecting their lifetime. Rydberg atoms of low angular momentum have a finite lifetime of the order of tens to hundreds of microseconds, which may be a limitation for this experiment. So indeed, they perform this very nice quantum simulation experiment. And I would like also to mention another platform where the basic method of preparation of the simulator is kind of different. Instead of using atom prepared in optical lattice by using the Mott insulator technique, indeed in the team of Antoine Brouwers in Saclay and in the group of Michel in Harvard, they use the optical tweezer technique. So basically, they use a laser field focused with a very large aperture lens over a dimension which is a fraction of the wavelength, a fraction of the optical wavelength. And in this way, they fabricate an optical trap, which is very similar to the one introduced and discussed by Juliette. So it's a dipole trap for the ground state atom, which can be filled if you put a cooling laser around the trap. And then the trap is so small that only a single atom can be there. If you want to make two, there is not enough room in the trap for two atoms, not because the atoms are too big, but because the atom will interact and will have a so-called light-assisted collision. They will form very fast a molecule, and a pair of atoms will be just eliminated from the trap when it forms a molecule. So in optical tweezers for atoms, when you load them with laser cooling, you basically have either 0 or 1 atom. And then you can look at the tweezer. And you can indeed look at many tweezers in parallel. So in this experiment, they have something like 100 tweezers initially randomly filled by atom with a probability of 1/2. And there is either 0 or 1 atom in each of the tweezers. So the dots which are not, indeed it's a regular lattice, and the black region correspond to tweezers which are not filled. But it's fast to image such an array of ground state atoms. And once you image them, you know where the atoms are. And then you can start a game which consists in moving the atom, again with optical tweezers, to rearrange them and in a smaller structure, which is compact with no defect. And you check by looking at it with a camera that there are no defects. And this is fast. This takes tens of milliseconds. So you can really have an array of very well-controlled sample of single atoms, up to something like 50 atoms in the present experiment. So that's the initial state of the simulator. It looks very much like the Mott insulator, but here it's even more deterministic. The probability to have a mistake, a missing atom, is 0, because basically, if you have an error, you see it and you correct it with tweezers. So it's very, very efficient way to produce this structure with high fidelity. And then the distance between the atom, which indeed is a way to adjust the strength of the interaction, can be varied by moving the tweezer at larger or smaller distances. So typically the distances here are in the range of a few micrometers, so larger distance than in this system. And then they use stronger interaction by using direct resonant excitation to the Rydberg atoms. So the resonant excitation allows them to switch on and off the interaction by putting the atom in the Rydberg state. The interaction starts, and eventually, after some interaction time, with a laser pulse, they can put back the atom in ground state and look at fluorescence to measure what happened. So in this experiment, they got very impressive results. I don't want to make a review about the experiment. And indeed, one point is that this simulator is very efficient because it is very fast. Typically, it's like if the elementary clock of the simulation, the elementary time scale of interaction, was a fraction of microsecond. So it's fast, means that decoherence is not so important, that the lifetime of ordinary Rydberg atoms is enough. But one limitation, and that's the limitation we would like to overcome, is that it is fast, but it cannot last very long. It does not last very long because in this simulator, basically, they switch off the trapping when they excite the atom in the Rydberg level. And then the story is that the simulation starts, but the motion of the atom starts also to play a role. Due to van der Waals interaction, Rydberg atoms repel each other and are just leaving the trapping site. And then the distance between the various the various Rydberg atoms varies as a function of time, and the simulator is not anymore under control. So if you want to perform simulation at time scale where motion is negligible, yes?
Why did they do not the tweezer?
Why?
Why did you not the tweezer?
Okay, they do not use the tweezer because these tweezers are operating with focused laser beam, and it's anti-trapping for Rydberg atom. So it's not trapped in this kind of tweezer. You have to use another kind of tweezer, but I will give more details about that just later. So the other point is that it's related to that. You could try to trap them in tweezer, but then the tweezers for Rydberg atom have trapping strength, which is not very strong as compared to the van der Waals interaction. So if you want to use tweezer, you have to relax the interaction by putting the atoms more far away. So then the complication becomes shorter. And then lifetime of low angular momentum Rydberg atom is not long enough. That's another limitation. So let's consider these two kind of experiment in which basically the simulation is fast, sub-microsecond time scale, but the number of cycles you can perform is limited by a few microseconds, which is the time needed for the atom to start moving and just changing the interaction strength. So what we propose is to go further by using much longer-lived Rydberg atoms, so-called circular Rydberg atoms, and by trapping them, in addition, in appropriate light structure. So here I recall you some interesting properties of the Rydberg atom with respect of this experiment. So as I just mentioned, the low angular momentum Rydberg atoms with sp or d orbital quantum number. So this is the quantum number L, which has value 0 for S state, 1 for P states, and 2 for D states. So that's typically the kind of level you can access directly with laser, with either 1 photon, 2 photon, or 3 photon transition. And for this level, the lifetime, the radiative lifetime is a range of up to like 100 microseconds. And then if experiment is performed at room temperature, this lifetime may be further reduced by blackbody radiation effect. So that's another limitation to duration of computation with respect to motion of the atom, which is the other strong limitation. So with the circular atoms, as you already know from the cavity QED part of my lecture, spontaneous emission is much longer, tenths of millisecond time scale instead of hundreds of microseconds. And in addition, and I will discuss this in more detail, spontaneous emission can be suppressed with a very high efficiency so that the time scale on which one can envision simulation is not microseconds, but seconds. The larger bit of the circular atom makes a strong dipole coupling interaction. And in addition, they are very nice because you can trap them with light without ionizing them, which is not the case for low angular momentum Rydberg atoms, which are much more sensitive to photoionization, which at some point becomes the limit of the trapping time for the low angular momentum Rydberg atoms. So let me tell now a little more precise property about the dipole-dipole interaction between the circular atoms. So here again is the two dipole interaction Hamiltonian. And how does it manifest on the energy level of the atoms? Well, it depends on the atomic levels you consider for the Rydberg atoms. For example, if you have two Rydberg atoms with same principal quantum number, indeed in the same quantum state, so both in NC, both in the same circular state, then you can see easily that the matrix element of R are 0 if you take it between 2 times the same state, because basically the R operator is an odd operator, and its average value is 0 in any quantum state of the atom. So you have no first order coupling through this Hamiltonian inside for this level. But if you go to second order of perturbation theory, then you can couple the circular state to other levels with different n and different L. And then if you apply the Hamiltonian twice, you have a second order coupling which just shifts the energy of this level. So the shift is the usually well-known van der Waals shift. So as its second order is scales at the square of the potential. So it's 1/R6, the spatial variation of this, and some coefficient at the numerator, which is traditionally named the C6 coefficient, characteristic of the strength of the van der Waals interaction between these two levels. Of course, it depends on n. So, of course, in a simulator, you don't want just a level, you want at most two to simulate a spin system. So let us consider a second state, another circular state with a different principal quantum number. Here you can see that you have two degenerate states here. If you put the excitation n prime either on the second or on the first atoms. Of course, there's two states, there's two quantum states at the same energy. And then you can eventually have a first order coupling between these two levels due to the van der Waals interaction. Indeed, if you choose n prime equal n plus or minus 1, you effectively have a first order coupling which is large, 1/R3, and which will dominate the van der Waals interaction. Indeed, for the simulator, it's interesting to have the van der Waals interaction and indeed the exchange interaction which will be created by the dipole coupling between these two degenerate states of the same order of magnitude. That's why we will choose for our simulator the situation where n prime equals n plus 2. So in this situation, the coupling term between these two levels is also a second order term with respect to van der Waals, with respect to dipole Hamiltonian. And then you create a matrix element coupling these two states, so which creates exchange of the excitation between the two atoms, which also scales as 1/R6 with a coefficient A6, which in magnitude is kind of comparable with respect to C6, and that we will have the possibility to tune by applying external electric and magnetic field on the atom. So in practice, n plus 2 are chosen like n equal 50 and n equal 48, not just because we are used to excite and to manipulate the n equal 50 circular Rydberg atoms, but if you go a little bit more into the details, you find out that if you increase the principal quantum number, then you reduce the frequency of the transition, and then you have more and more blackbody photons in your environment, even if you are low temperature. At a given temperature, if you increase n, you decrease frequency, and you have more blackbody effects. So this is not good. If you go to smaller n, then the strength of the interaction decreases, and then your simulator is slower. And it's not good in the same kind of way. And at some point, you also have less flexibility on the tunability of the interaction parameters. So then, which kind of Hamiltonian can you build out of this two-body dipole-dipole interaction? Indeed, now I don't consider just anymore a pair of atoms, but a chain of atoms in a linear configuration, so a linear chain of spin. And here is the Hamiltonian we will be able to simulate. So I will comment separately the various terms of the Hamiltonian, starting with the simplest one, which are these two terms, which are just single spin terms. And indeed, this is proportional to sigma z and some parameter delta. So this is equivalent to the Zeeman effect in the magnetic field, which is parallel to the z-axis. The second term is proportional to sigma x, and it's equivalent to a transverse magnetic field applied to the field. So in practice, we will not apply and vary an actual magnetic field to control this term in the Hamiltonian. We rather prefer to add what we call microwave dressing of this two-photon transition between the Rydberg atoms. So it means that we have a microwave source from outside that we shine of these atoms. And indeed, if we tune the detuning of the source with respect to this transition, in a properly chosen rotating frame, this amounts to create this term of the Hamiltonian, with here the detuning playing the role of the magnetic field along the quantization axis Z. Then the strength of the microwave, the Rabi frequency associated with this microwave, plays a role, again, in the rotating frame of a transverse magnetic field. And having a way to adjust these two parameters for simulating solid-state physics is important. Usually, when you study spins in solid-state physics, you apply magnetic field in addition to interaction, and you have to vary them to explore the phase diagram of the system. So here, both of these parameters are adjusted by adjusting mainly the detuning of the dressing microwave source and the Rabi frequency, so the power of the microwave field you put to the atom in order to dress these two photon transitions. So then comes the more interesting and more complex term describing the interaction. So here I choose to consider only the next neighbor interaction, as the interaction I am considering is the van der Waals interaction, scaling as 1/6. The second next neighbor interaction is like 64 smaller than the other and can be, as a first approximation, neglected. So next neighbor interaction here have two terms, the so-called Ising term, which couples the Z component of two neighboring spins. And it is characterized by a coupling constant, which is here represented by GZ. So the other, and this term is basically the fact that the energy of one of the spin, the difference of energy level of one of the spin, depends whether the other points in the upper or the lower direction due to van der Waals interaction. So the last term is related to the exchange part of the Hamiltonian, which coupled the down spin state of one atom with the up spin state of the other, basically. And so it's a term which can flip the spin. And here we write it as a function of the transverse component of the spin, sigma x, and sigma y. And here again, it is characterized by coupling strength, and that I denoted here by G. And indeed, both these terms can be, the strength of this term can be varied, and that's an interesting property of the Rydberg atom. One gets controllability and tunability of the coupling by applying to atom both an electric and magnetic field, both parallel to each other and setting the direction of the quantization axis. So if you look into the details of the calculation of the coupling strength, so it's big numerical calculation where basically you diagonalize numerically the dipole Hamiltonian between two atoms as a function of distance, and from the variation of energy levels, you get the strength of the van der Waals and the exchange interaction. And you can design, you can then compute this interaction, and you can represent the relative strength of GZ component with respect to the G component of the Hamiltonian as a function of the amplitude of the electric field applied to the atom for a given magnetic field. Of course, you can do the calculation for other magnetic field, but this is interesting because for a very reasonable range of electric field, from 6 to 11 volts per centimeter, so much less than what is needed to ionize the circular Rydberg atom, you can vary the ratio GZ over Z in an interesting range, which varies here from minus 0.5. So the important thing is that this is below -1, up to plus 1.5, which is above 1. And you can even go further away if you vary slightly the magnetic field. So why is this interesting? Well, this range of parameter variation is related to the range of parameters where the physics of a spin 1/2 is interesting, and it maps, it allows to explore the phase diagram of a spin 1/2, of interacting spin 1/2. So for example, if you have equal interaction here and here, it's kind of isotropic interaction between the spin. And there are theoretical predictions about what is the phase of the system along this dotted line. If you have opposite sign but equal magnitude, basically formally it's completely equivalent to the isotropic model. If you go to this point, GZ goes to 0, and you have just only the transverse coupling. And then it's what is called pure XY interaction. The Z term vanishes. On the other hand, if you would like to have GZ dominating, no, okay. So, and last point is also an isotropic interaction model. So what is the strength of the interaction? The strength of the interaction, of course, depends on the distance between the atoms. So a typical distance for the kind of trapped Rydberg atom we plan to prepare is like 5 to a bit more micrometer. Then the G coupling constant is like 17 kilohertz, which makes the exchange time, which is given, you have it's 1/4G. Then it's a range of 10 microsecond time scale, which means that the typical frequency at this distance, which is compatible with trapping, the frequency of operation of the system is like 100 kilohertz. So this is interesting because I will show you that we expect to trap the atom for 1 second. We can have like 40 atom chain with something like 10 to the 5 exchange time before you lose the first atom due to imperfection related to residual spontaneous emission. So that's something we can expect to do, exploring the phase diagram with this system. So here I represented a more complete view of the phase diagram of this spin 1/2 Hamiltonian, so which is a so-called XXZ Hamiltonian. And I will comment about this in 1 second. So indeed, this is kind of symbolic phase diagram, which was qualitatively well-known for a very long time. And we started a collaboration with a guy which is an expert of solid-state system and of numerical method for describing many-body solid-state systems. So Guillaume Roux, which is in Paris-Saclay, who was able, by using DMRG techniques, to reconstruct this phase diagram numerically. So what is interesting in this phase diagram? So you have several regions corresponding to several phases of the system. The horizontal axis omega is like the transverse magnetic field. And here, the diagram is represented in a simple situation where delta equals 0. Of course, something may happen also if you vary delta. But for delta equals 0, this is already interesting. So the horizontal axis is omega, and the vertical one is GZ over Z, the parameter I can vary with electric and magnetic field. And here you have, for example, kind of simple phases, like a ferromagnetic phase. So in this ferromagnetic phase F, all the spin point in the Z direction. And it exists as soon as the transverse field is not large enough. When you increase the transverse field from this F phase, you reach what is called a PX phase, which is a phase where all spin point in the Z direction. So this one is kind of intuitive. It applies a strong transverse magnetic field in the X direction. At some point, the ground states correspond to all the spin aligned on the magnetic field. If you go upwards, you have two other interesting phases, and you go to these phases where you cross the green lines, which correspond to the isotropic interaction. So that's why these lines are of importance. So you first go to what is called the Niel phase in the Y direction, or a phase with what is called a stacked order, in which the spin points in the Y direction, but alternatively in a plus and minus direction. And NX is the same, NZ, that you reach when you increase GZ, is the same, but in the Z direction. So spin pointing alternatively up and down in the shape. So this kind of thing is well known because basically it can be efficiently drawn by using DMRG techniques, which allow to characterize the ground state, to calculate the ground state of the system very efficiently, and so to design the phase diagram which reflects the magnetism, the magnetic properties of the ground state of the system. So what is more tricky, even in a one-day system, is to predict what happens if you do some dynamics, if you vary the parameters. And here you should have in mind that all the parameters of this Hamiltonian can be varied very fast. The detuning is set by the detuning with a microwave source. So you have synthesizers which have the frequency which can change very fast. So you can change the longitudinal field very fast. You can switch on and off your source very fast, which means that the transverse field can be switched on and off very fast, which is not always the case with actual magnetic field. If you have to apply magnetic field, you need some coils, they have some inductance, and it's eventually not so fast to vary transverse magnetic field. So here it's fast. Then for GZ and G, as it strongly depends on electric field, going in this direction is also a kind, going in the vertical direction is also a kind of easy. So just in order to show you the kind of thing we can study with this system, maybe as kind of a benchmark for exploration of this phase diagram, we made, together with Guillaume Roux, a numerical simulation of what happens when you go back and forth through a phase transition. And when you try to go back and forth kind of adiabatically, so that the system will follow the ground state of the spin system, in order to prepare the ground state in this phase, knowing that the trivial phase to prepare with the laser when you prepare the circular atom in a given state is the F state, the F phase. And one of the ideas is to study numerically the effect of one eventual imperfection of the experiment, which is the residual motion of the Rydberg atom. So laser preparation technique of trapped Rydberg atom should lead to very small residual motion, but not zero temperature. And then if the atoms are moving, of course, the coupling are just submitted to noise as a function of time, which may just destroy adiabaticity in this kind of process. So it's interesting to have a look at this. And that's we perform a simulation of the evolution of the system. So this is a simulation performed numerically for 40 spin in interaction, which is still small enough so that you can diagonalize the Hamiltonian. And here is represented various magnetic properties of the system as a function of the trajectory from F to P and then P to F. So you have on the first graph the magnetization along the Z-axis. So in the F phase, all the spins are supposed to be aligned to the Z-axis, and then in the initial state, mz equals to 1. On the second graph, you have the magnetization along the x-axis, which is supposed to be 1 or minus 1 in the px phase, in the paramagnetic phase. And then the blue line represents the value of mz and mx as a function of time. And during time, you vary the coupling coefficients, you vary omega by using this profile. You increase it and decrease it, and you vary the velocity so that you are kind of adiabatic when you cross the phase transition line. So you see the blue line is describing the property of the perfect system with polarizability along Z for t equals 0, and with spin pointing in the x direction when you are at the top of the sequence where you go back and forth through the phase transition. So then you have two other lines, which are the interesting one, which corresponds, first, the red line corresponds to the calculation, numerical calculation of adiabatic evolution. Indeed, that's explicit integration of the Schrödinger equation without atomic motion. So for perfect lattice of spin at fixed position. So you see that the red lines prepares the parametric state kind of efficient way with some oscillations, which means that even if you optimize the rounds, it's not completely adiabatic. If you add the motion, then you see that it's much worse. When you go cross the transition and bath, the red line, for the red line, it's already difficult to go back to the initial state, but the polarization is even smaller if you have some atomic motion. So you could say, okay, for having a better red line, just go slower to be more adiabatic. And at some point, if I go slower and slower, effectively the red line goes to the blue. But at the same time, the black line will be worse and worse, because if I go slower and slower, I have more time to shake the chain, and the noise is completely detrimental for the thing. So the parameter chosen here for the ramp are kind of optimizing what you can get in the case of motion, which is a case where you have to sacrifice a little bit the adiabaticity in order to keep a reasonable or a non-zero fidelity of the system with respect to the ideal case. Indeed, the last graph is a variation of the fidelity with respect to ideal case. So, of course, the blue line, by definition, is fidelity 1. The red line is the defect of adiabaticity in the regime where the time you get is limited by the fact that you want non-zero fidelity with shaking. So here it seems not very good, but it is related to the fact that you have a kind of coincidence between the coupling strength between the spin and the oscillation frequency, the mechanical oscillation frequency of the system, which are calculated by calculating classically the motion of the atom in the trapping potential. So if you go with slower interaction, so you switch the coupling from 17 to 2.3 kilohertz, then everything goes much better. So you see you cannot anymore distinguish the red, the blue, and the black lines. Everything is like perfect. As well for the polarization along Z, as for the polarization along the X direction, and then the fidelity reaches a very, very good value, like 0.995 here, even in the presence of motion. Of course, you see here that the two fidelity scales are very different. So it means that one could worry in this system about the degree of control of the atomic motion you need to well-controlled quantum simulation. Indeed, here you see that indeed motion is not detrimental, provided you adjust the coupling strength of the spin to be non-resonant with the frequency which are present in the motion. So G equal 2.3 represents a coupling strength in the range of 10, a little bit less than 10 kilohertz, which at the time scale of 1 second, which will the one on which we expect to operate, is like 10 to the 4 elementary time of the spin flip process, which is quite a large number. So here I put again the same figure corresponding to the slower dynamic with the written conclusion so that you can have them in the note. And now I go again to the general form of the Hamiltonian, just to kind of propose first list of quantum effects which could be studied in this system by varying the parameters as a function of time in a various way. So I already talked about the exploration of the phase diagram by adiabatic variation of parameters as kind of benchmark of our ability to navigate there and to prepare all of the interesting phase of the system. Then we can explore time variation and motion in this phase diagram, which is in a non-adiabatic regime, so-called studying quenches. And basically, many interesting effects are related to quenches. For example, you can study the rate at which you generate defects in the system when you cross phase transitions. So that's the so-called Kibble-Dirac process. But there are many other things to explore in this direction of quenches. You could study transport in the chain. You can eventually study medibody localization in a chain with a control disorder. When you trap the atom, you can put disorder in the distance between the atoms by distorting the trapping potential, and this is a tool for exploring this. You can also build not just spin chain, but a spin ladder by having two parallel chains of spin, and then goes in the direction of the physics of spin is in 2 dimensions. Indeed, here it's not real 2 dimensions, but you can build effective spin 1 out of pairs of spin 2, 1/2, and then use this for studying the Haldane phase and the Haldane physics and the physics of topological system with this kind of simulator. So this is some perspectives for eventually far away in time. And now I will tell you a little bit more where we are in terms of practical realization. How can we answer the various requirements for building a good quantum simulator by using these trapped circular Rydberg atoms? So one first element of this simulator, as told you, is the long interaction time. At the time scale, which have to be in the range of seconds, which is much longer than the usual radiative lifetime of circular Rydberg atoms. So I already told you that this lifetime is a range of tenths of milliseconds, but now we will look a little bit more into the details in order to understand this number, 25 milliseconds. So what is the transition which is responsible for this finite lifetime? So let's assume that we prepare the lower state of the spin involved in the simulator, so the 48 circular Rydberg state, which is coupled by a microwave one-photon transition to the 47 circular state. And in this transition is delta m equal 1. So it is a dipole low transition. And indeed, the lifetime here is the lifetime determined by this single transition, a dipole emission on a transition at a microwave frequency. And this is the reason for which, indeed, circular atoms have a long lifetime. This transition is the only transition coupling the circular atom to lower lying levels due to the selection rule of electric dipole transition. On the other hand, if you were not in circular state but in low angular momentum, you could emit optical photons, which are responsible for the short lifetime of the low angular momentum Rydberg atoms. So here, lifetime is long because basically you have only one decade channel, which is a microwave channel, and spontaneous emission rate is slow if the frequency of emission is a low frequency. And you can even do better because as you have only one transition, you can try to contradict spontaneous emission by changing the density of mode of the electromagnetic field at the frequency of this transition. And here there is a well-known way in atomic physics to suppress the mode at this frequency. So this was this is a reference to a pioneering work in the team of Dan Kleppner at MIT about this, where he observed already with circular atom inhibition of spontaneous emission. So the idea is to put the atom in a very simple structure, not a cavity, but just two parallel plates forming a capacitor. And when the distance between the two plates is smaller than half the wavelength of this transition, you cannot fit any more electromagnetic mode for the spontaneous emission of the atom at this frequency. More precisely, if you have well-oriented circular atom like this with an electric field perpendicular to the plate, which is a natural electric field you can apply to the atom between two plates, then the dipole oscillating parallel to the plate have no coupling to empty electromagnetic modes because the electromagnetic mode polarized parallel to the plate are suppressed by the conductivity of the plate. And then this suppression can be very, very good. In the initial experiment, it was already several hundred, but the demonstration was performed on atomic beam at a very short time scale. Indeed, the suppression can be very good at the scale of thousands, up to scales of thousands of seconds. And indeed, we made a numerical simulation of the rate of radiation of the dipole oscillating parallel to the plate as a function of a distance to the plate and as a function of the size, the transversal size of the plate. And both sides here are represented in unit of millimeters. And you see that we choose a plate separated by 2 millimeters, which is kind of a macroscopic distance, with a size of the order of 15 or less than 15 millimeters. The inhibition rate is several thousand. The initial emission rate is like minus 50 dB. And if you translate this into time, it's like 2,500 second lifetime in such a very reasonably sized capacitor. So potentially, the spontaneous emission inhibition is really very efficient tool. And if we take into account imperfection and residual effects, you can expect a lifetime as long as 10 minutes for a circular atom between two plates. So that in itself would be a very interesting experiment. So then, once you are able to have the atom lifetime increased to thousands of seconds, it becomes extremely interesting to trap them because at the scale of seconds, the atom just have time to fall. And then it's a very good thing that indeed there is a nice laser trapping scheme for circular states which basically have the same polarizability with respect to laser as a free electron. So if you put a strong focused laser on a Rydberg atom, it basically behaves like a free electron with respect to the force which is exerted to the atom. The force indeed is named the ponderomotive force. It is known in plasma physics, for example, as a ponderomotive force. The point is that this force is a repulsive force, so it expels the electron from the region with high intensity, so that if you want to trap a circular atom, you have to create a minimum of the intensity at some position of space, which can be done by using hollow laser beam. You can have some beams which are not Gaussian beam, but for first order Lager Gaussian beam, for example, have a phase variation around a circle which is 2 pi phase shift, and it creates a hole at the center of the beam. So in such a beam, you can trap Rydberg atoms, and it's efficient trap because polarizability is comparable to that. Polarizability of a free electron is comparable to that of a ground state rubidium atom in experiments where you use optical dipole trap in order to get them. So basically, the trapping strength is comparable to what you have when you use ground state atoms. An important feature of the trapping is that it is also, for nothing, it is given as kind of independent of the principal quantum number of the atom. So in terms of quantum simulation, it's very interesting in terms of coherence time, because it means that even if the atom does not sit exactly at the center of the potential, so if it experiences light shift, then both levels of the simulator, the 48 and 50 circular state, will have the same light shift, which means that the superposition of the two levels will have a very long coherence line. So basically, it means that this kind of trapping of Rydberg atom is automatically at a magic wavelength, whatever the wavelength is, because both levels are shifted in the same way by the trapping potential. So this is a good feature. It's not perfect, because if you go into the detail, you find that depending on the principal quantum number of the Rydberg atom, the size of the atom changes, so that the atom averages more or less the potential, but this is a very small effect. Last very interesting property with respect to low angular momentum Rydberg atom is that photoionization is completely negligible for circular atoms. And this could be a very strong limit. If you plan to have an atom trapped for, let's say, 10 minutes, if it photoionizes after 1 second, you are lost. You are lost. And indeed, low angular momentum state would ionize well before that. But it appears that circular atoms have photoionization rates which are completely negligible at the scale of the experiment, and that's related to properties which are very well known, because basically circular atom is like hydrogen, so you can compute exactly the rate of photoionization of a circular atom, and the number you find is like the overlap of the circular wave function, which is huge, with the function, the wave function of the electron, which is ejected from the atom at high energy, which oscillates very fast, and which just averages to 0 when multiplied by the wave function of the circular state. So this is a very important property. These atoms can be trapped and will not be destroyed by the trapping, even if they are close to the ionization limit. So then, what structure can we plan to use for laser trapping the system? So for building the spin chain, an interesting structure which should be compatible with inhibition of spontaneous emission is presented here. So it consists in an horizontal beam here, which is the hollow beam, the beam with a hole at the center, so that the atoms can be trapped in a tube. And of course, it's not enough, because this does not provide trapping in the direction of the beam. And what we plan to do is to add an optical lattice, a one-dimensional lattice with the same axis as this trapping beam, which can be fabricated with adjustable spacing between two lattice sides by making two transverse beams interfere at the region of trapping with adjustable angle. And if you adjust the angle, you can adjust the distance between the atoms here, between 5 to 7 micrometers, which typically are the numbers of interest for the experiment. Then you can estimate the efficiency of trapping by estimating the frequency of oscillation in the dipole trap, where each atom will be confined. And it's typically like 20 kilohertz, the trapping frequency in the longitudinal direction, and slightly lower trapping frequency in transverse direction. Then this trapping frequency can be made comparable as soon as you put enough power in the hollow beam. So in practice, 1 watt of power is fine for having very high trapping frequency. Of course, for dealing with such power, you have to take into account the fact that the experiment will be performed in a cryostat at a temperature of probably less than 1 degree Kelvin. So you have to be very careful about the losses of the trapping beam, and eventually not use a watt, but maybe 100 milliwatt with which one can deal with. But with power compatible with the cryogenic environment, you can have such kind of trapping parameter which are very reasonable for the experiment. So when you put the effect of both the capacitor around the atom, the trapping laser, the interaction between the atom, you can make a very precise analysis of many parasitic effects which may reduce the lifetime of the atom in the trap. So here is the budget about this lifetime issue. So at the top, there is the longest time scale, which is stated by what I already mentioned, the efficiency of inhibition of spontaneous emission by a capacitor for a single atom at 0 temperature. So you can then add one effect like the contribution of residual blackbody radiation, which indeed will create upward transition from the Rydberg level, which are eventually not inhibited by the capacitor. So this reduces the lifetime to 600 seconds, typically 10 minutes, so that's the 10-minute limit for a single trapped Rydberg atom. Then an important level is this 88 seconds, which is due to interaction. When you put two atoms at 5 micrometers from each other, with the quantization axis, which is vertical, set by the electric field, you have a contradiction between quantization axis and interatomic direction, which means that the interaction between the atom will mix a little bit the circular with elliptical level, and inhibition of spontaneous emission is not perfect for elliptical level. So as a consequence, the lifetime is reduced, but it's still reasonable. Then you can study some effects which are known for magnetic atom as dipolar relaxation. Basically, it does not exist there. Photoionization does not exist. Collision with background gas. Here we benefit from the fact that inside a cryogenic environment, there is basically no background gas, so no collision. So if you estimate somehow, because it's very difficult to measure the vacuum in a cryo, like 10 to the minus 14 torrs of millibars, this sets the limit to 400 seconds, which means that if it were not in a cryogenic vacuum, you get into trouble with this number. Then elastic diffusion of photons, of trapping photons. The laser has a lot of photons which may be scattered by the Compton effect on the Rydberg electron, and this may destroy the coherence of the circular atom. So this limit is also a large number, like 180 seconds or larger than that. So that in the end, typically, you expect to be able to trap a single circular Rydberg atom for 1 minute in the trap, which means that if you have like 50 atoms in the trap, you don't lose one before 1 second. So that's the reason why one of the goals of this experiment, the figure I choose as a goal for the time scale of quantum simulation is 1 second. 1 second is reasonably reached with this system up to 50 atoms in interaction. So last important technical aspect, the preparation of the initial state of the spin. You have to fill a lattice with a 100% efficiency with exactly 1 atom per side. So how to do this? Here is a method we proposed so in a recent Pierre's paper that presents the ensemble of the simulator, which basically consists in starting the trapping experiment, not with the full structure. Basically, we don't put the lattice on the atom. We put the tube of light so that the atoms, the Rydberg atoms, which are prepared very fast at the right place, are trapped initially. And then we close the trap just at the end by 2 transverse beams which just are closing the bottom. So we choose one of the beams with a power slightly smaller than the other. And then we imagine that you can change the distance between the two plug beams by using some optical modulator. Basically, you can try to compress the chain. Initially, the atoms are prepared randomly by laser excitation with distances between various atoms which are just random. But as soon as you start to compress them, you will enforce some order due to the competition between compression and van der Waals repulsion between the atoms. The circular atoms have a repulsive interaction, van der Waals interaction, if the circular orbit is oriented parallel to the plates here. So you push, you pack the atom, and at some point, the thing becomes so compact that the repulsion of van der Waals is stronger than the trapping force. And you start to eject the atoms one by one. And in this provides evaporative cooling. And this is indeed a very efficient way to prepare a chain with a very well-defined, very well-controlled number of atoms and very low temperature. So I will not give you all the details about that, but we simulated the motion of the atom during evaporation by numerically integrating the equation of motion of the atom. So it's a classical model. And indeed, what you see on this graph is that as a function of distance between the two plug beams, the variation of the average photon number in the trap between the two plug beams. And you see that if you start with like 100 atoms, which is not represented here, as a function of length between the two beams, the number of atoms reduces, evaporation proceeds. But here, around n equals 40, if you zoom in into the curve, you see that you have plateau where the number of atoms have no fluctuation. It means that the temperature of the atom is cold enough so that the photon number, the number of atoms, the fluctuations are not enough to blur the number of atoms by evaporating the last atom at random position. And so if you stop the evaporation exactly there, you will have exactly 40 atoms in the chain. And if you make an estimate of the temperature, it looks very efficient. If you start with atoms in the ground state at 1 microkelvin, if you excite them to Rydberg state basically by a pi pulse, you will not hit them. And then if you evaporatively cooled a chain of about 100 atoms at the beginning, in the end, the residual motion in the potential well, once you add the lattice, is like 2 to 4 quantum of oscillation in the ground state of the potential. So indeed, the chain is supposed to be prepared very close to the ground state, the quantum ground state of motion of the chain. Of course, you could say that this model is a classical model of the motion of the atom, so it may be not valid in the quantum regime, but indeed in collaboration with David Papoular at the University of Paris-Cergy, indeed we made a quantum description of the evaporation process, and there is recently a paper on arXiv we posted on this topic, which effectively shows that the quantum model predicts very, very small residual motion of the atom after the thermodynamical modelization of the evaporation process. So this seems to be a very efficient way to have a chain without defect, and the fact that you don't have defect does not rely on rearrangement and correction, but it's built in by the fact that you pack the atom together, and by definition, if one atom is missing, the other will just go there, and there is no hole in the chain when you push. So what is the present status of the experiment? Well, we are already just at the beginning, and we constructed this experiment from an experiment constructed already some time ago in our group to have ultra-cold atoms in a cryogenic environment with the idea to make Rydberg atom out of them. So we had such a setup where we were able to prepare eventually a Bose-Einstein condensate of rubidium using some atom chip techniques. So here you have a superconducting atom chip where you have superconducting wires generating some magnetic field structure to magnetically trap the atom and eventually perform evaporative cooling of ground state atom down to BEC, which can provide a very good stores of ultra-cold atom as a starting point for the experiment. So then we plan to implement the various elements of the experiment, and the first thing we implemented is the laser trapping. So in the first demonstration experiment, we add parallel to the atom chip a laser beam, which is indeed an infrared laser with a wavelength of 1 micrometer something, and which is like up to 10 watt laser, which is sent through the cryostar. So we have a cryostar with temperature of operation is 4 Kelvin, which is compatible with having 10 watt crossing the cryo for performing the experiment. And then we adjust the geometry of the system so that the laser used to excite the Rydberg atom, which is a combination of blue and infrared laser. So the blue laser is focused just at the center of the trapping beam, which is a hollow beam. And then once we prepare the circular Rydberg atoms there, we detect them after trapping in the usual way by looking at time of flight of the rubidium ion, which I created after field ionization of the Rydberg atoms. And then these rubidium ions are directed to a channeltron detector, which allows us to count them. So what we do in order to demonstrate trapping is kind of indirect thing, because basically we don't have spatial resolution. We don't see with this detector, which is kind of 1 pixel detector, the shape and the position of the Rydberg atom. So we have to develop a trick which is just the same thing as you do where you do magnetic resonance imaging, ERM, for looking at what's inside your body. Instead of putting a gradient of magnetic field, we apply a control gradient on electric field on the atom, and then we induce microwave transition. And indeed, inducing microwave transition in gradient amounts to probe the atoms, the Rydberg atoms, at different positions. And basically, by looking at the evolution of the width of the microwave resonance as a function of trapping time, we observe these two curves. So what is the meaning of the width of the microwave resonance line? If it is large, and if it becomes larger and larger, it means that the atom expands and explore larger and larger regions in the gradient of the electric field. So they explore large regions, they explore large gradient, and the line width of the line increases. If you switch on the trapping, you just suppress the broadening of the line. The atom just stay where they are prepared, and I think that it's a very good demonstration of the trapping. So the red line is what you expect from the knowledge of the temperature of the atom. So we already detect by looking at the way the line gets broadened, we detect the way the rate at which the atomic cloud of circular atom just expand. So it's a kind of time of flight measurement for the Rydberg atom, and it's a measurement of the free expansion of Rydberg atom in the case of the red line. And this free expansion disappears where the atoms are trapped. So this is the first demonstration experiment. It is performed with a beam whose waist, the size of the trapping region, is like 20 micrometer. So for going to the experiment with inhibition of spontaneous emission, everything around, we have to use slightly smaller beam, like 6 to 10 micrometer size, but it's not very different. And it's a very good starting point for this trapping experiment. So I am about at the end of this lecture. So I would like also to say that all the story is not what happened between two plates with inhibition of spontaneous emission, which is kind of very challenging experiment. But I guess that, and I'm ready to bet that we can do interesting things with trapped Rydberg atoms, even without inhibition of spontaneous emission. So I'm sorry here, in this figure, inhibition is there. But we could envision, instead of the kind of complex evaporative techniques I described for preparing the atom, have a more straightforward way to have atoms not directly in a tube, but in an individual optical tweezer. And that's a project that we are running first. The idea is that if you start with ground state atom in optical tweezer, as Lukin or Brune are doing, as we are able to very efficiently prepare the circular atoms with probably close to 100% excitation efficiency, we could switch the trap from a trap from the ground state, so a Gaussian trap, to hollow trap once we excite the circular atoms and have the circular atom trapped in tweezers even without inhibition of spontaneous emission. And probably we cannot have as many atoms as there, but we can start much faster to do something and to perform simulation, not at the time scale of a second, but maybe at the time scale of tenths of millisecond, which is not so bad as compared to the existing experiment. So I will conclude this series of lecture with that slide. And before going to the question, I would like to mention all the peoples which were involved in the work I described during my lecture. So I would like to stress that the cavity QED project with circular Rydberg atoms was kind of long-term project, and all the people here in red, purple or red are people which were involved in this cavity QED experiment. So you can recognize Brazilian people, and among them Raul, in the list of the people involved in this work. Luis Davidovich and Nissim Zaguri from Rio had a very long and very fruitful collaboration with us about the cavity QED experiment. And so the time scale is that this cavity QED experiment started basically in 1991 when we proposed theoretically in a paper, in a physical review later paper, the scheme for quantum non-demolition detection of the photons with the Rydberg atoms. And then it took some time to get to the nice quantum jump signal I presented in the lecture. The proposal was 1991, and the quantum jump signal was 2006, so a kind of bunch of time. But sometimes some experiment needs perseverance and time, and all these people had a lot of perseverance, and I would like to thank all of them with here a picture of, it's not very recent, I'm sorry, but basically, typically the recent group is like this. And I would like finally especially mention the collaboration with Serge Haroche and Jean-Michel Raymond, without whom I think I would not have been able to run such a project just alone. This is kind of project we need in times, and I think we need collaboration between many people. And I think it's important to stress at a time where usually when you have to make application to get money, you have to be a single PI, because people providing money think that everything can be done by a single guy, which is sometimes not so right. And just to finish, a little bit of advertising for this very good book if you want to learn more into more the details of the system I just described. So I thank you for attention, and we have time for questions about the quantum simulator. Yes?
If you are already using the plates to supply the spontaneous emissions, why do you need the cryogenic environment?
Okay, so cryogenic environment is needed because if you have black body photons, the one single decade channel picture I used is not anymore valid. And I will just tell you why. Okay, it's here. So at zero temperature, the atomic state can just decay like this. But if you have black body photon, you have also channels which can go upwards. And okay, if you imagine that you are not in 48 but 47, you can have an absorption of a pi polarized photon from here to this elliptical level. And pi polarization is not good because it's not suppressed by this structure. And then you have to take into account not only this transition, but all the upward microwave transition induced by black body photon at 50, 100, 200 gigahertz. And this causes some limitation. So not to be limited by that, you need a temperature which is like half a Kelvin. So it means that this is an important thing to reach such lifetime as I described. You need really much less than room temperature. You need even much less than 4 Kelvin. So you really have to be careful about losses due to trapping laser and all the stuff you need to manipulate the Rydberg atoms. Other questions?
Thank you, Michel, for the series of lectures.
Thank you, and thank you.
Okay, so we will restart at